Day 29 Notes, Advanced Algebra 2. Today we continue our discussion on factoring trinomials, and we spend our time starting with factoring using the greatest common factor, and then we spend a little bit of time making sure that we recognize when trinomials are factored completely. First thing that I want to remind you of is that when we factor, our objective during this unit is to see simple binomials when we're finished. So in other words, if I start with a problem x squared plus 2x plus 1, rather than leaving my solution as a trinomial like this, it's going to be much preferred to find the end result where we have two simple binomials side by side. In this case, that's x plus 1 and x plus 1, since this was a perfectly square trinomial to begin with. We could also consider this as a solution x plus 1 squared, since the squared binomial is the typical solution that we looked at for standard trinomials that happen to be perfectly square. In the first set of examples today, we're going to look for greatest common factors, or in other words, the biggest number that is a factor to each of the terms on the inside. So biggest is another word for greatest, and a number that's a factor to each term must be a common factor. So that's where the name comes from, greatest common factor. These first few examples come from the textbook. If you'd like a copy of the text, please let me know. Otherwise, I'm only going to provide you with sample problems to complete throughout the week. Here's the first example. We're being asked to factor the binomial, in this case, 3x plus 1. And sometimes this greatest common factor factorization is quite simple. What we're looking for is the largest number that divides both 3x as a term and 21 as a term. So the biggest number that can divide that is going to be the number 3. Since 3 is the largest factor, we'll write that out front of a parentheses or a grouping symbol here, and then we're going to indicate what's left behind after we factor out the 3 from each term. And so to factor out an object, that's the opposite of multiplying, so we're looking for basically what would multiply by 3 to return us back to this 3x. And so that happens to be an x here, and 3 times what equals 21? Well, that's a positive 7. So to factor 3x plus 21, we would show the answer 3 times x plus 7. Here's another example. If we have to factor the binomial 8x squared minus 6x, we might recognize that 2 is the largest number that divides both 8 and 6. So 2 is the largest factor for these two terms. When I factor a 2 from 8, that leaves me with a 4, and we'll leave this as x squared for right now. And if I factor a 2 from negative 6, that leaves me with a negative 3 and the x. So when numerically factored, we're left with 2 times the quantity of 4x squared minus 3x. Let's take a look at one more. Here we have 6x cubed plus 12x squared. The largest number that divides both 6 and 12, so the largest factor of the two terms that we have on display here, would be the number 6 itself. And after I factor out a 6 from the first term, I'm left with an x cubed. That's because 6 times x cubed is 6x cubed. For the second term, after I factor out a 6 from the 12, I'm left with a 2 and an x squared. And again, that's because 6 times 2x squared would equal 12x squared. And if we were factoring just numeric greatest common factors at this point, these would be fine solutions. However, problem 2 and problem 3 technically are not completely factored right now. We'll talk more about that in just a minute with this next example. Let's revisit that first problem, which I said was not completely factored, the 2 times the quantity of 4x squared minus 3x. Let's consider the two terms that we had to begin with, 8x squared and a negative 6x, and let's rewrite them in their prime factorization. You should remember from Algebra 1 that prime factorization means to list all of the factors of a particular term or value and list only the prime factors. So, for example, the number 2 times itself 3 times in a row would equal 8, and x times x equals x squared. The number 2 is a prime number, so that's why I list it here rather than saying 2 times 4, because 4 is not prime. But if I list 2 as many times as necessary to get to 8, that would be okay. In the next example, I have a negative sign because this was a negative 6, and then I have to list the prime numbers 2 and 3 because 2 times 3 equals 6. And in this case, we have just one x. By listing the prime factorization, we should be able to identify all factors that are common, not just numeric factors. So in this case, this answer actually should have been factored with a 2 and an x in front of the grouping symbol rather than just 2 as we had listed primarily, or in the first case. So let's show what that would look like with both the numeric and the variable common factor removed. We'll write the 2 and the x out front because there was a 2 and an x common to both. And then we'll list what's left behind. What's left behind after we factored out a 2 and an x from 8x squared is two 2's, which multiply together to make the 4, and 1x. And what's left behind from the negative 6x after we factor out a 2 and an x is the number negative 3. This would be a completely factored answer for the problem above. Let's revisit the other problem as well. 6x cubed and 12x squared. In this first case, the numbers that multiply together, the prime numbers I should say that multiply together to make 6, again are 2 and 3. And I have 3 x's that multiply together to make x cubed. For the 12x squared, I would have 2 times 2, which makes 4, times 3, which makes 12. These are the 3 prime numbers that multiply together to make 12, and we have 2 x's. Now we should be able to clearly see what the greatest common factor will be. I have 2 2's in common, I have 3's in common, and 2 pairs of x's that are common. So what we should be able to say here is that the greatest common factor should have actually have been not just 6, but 6x squared. And what's left behind in the 6x cubed is just this 1x, so we're left with x. And then from the 12x squared, the 2 is left behind, so we would say plus 2. And this would be a fully factored answer to that problem. This technique also works when we have a numeric factor and multiple different variables for our factors. So let's try factoring this problem. The trinomial in this example looks awfully involved because it's got 3 terms and each term has many different variables, or at least 2 different variables with it. But if we use the technique that we listed above, we can still find the greatest common factor and do so relatively easily. So I'm going to list my factors again, my terms again, 12x to the 4th y squared. Then I'll write negative 6x squared y cubed, and then I'll write 15xy squared down below my original trinomial. Then we'll create the prime factorization for each. So the prime numbers that multiply to make 12 we saw before are 2, 2, and 3. And for x to the 4th, that means we have 4 x's written side by side. 4 x's multiply together to make x to the 4th. And for y squared, that's 2 y's multiplied together. For the number negative 6, we have negative 2 times 3. And for x squared, we have x times x. For y cubed, we have y times y times y. Lastly, two prime numbers. There are only two prime numbers that multiply together to equal 15, and that happens to be 3 times 5, so that's the prime factorization for 15. We have 1x and 2 y's. And this is the list of the prime factorizations of each of our three terms. So now let's just find numbers that are common to all three. So as far as our numeric values go, the only thing that's common to all three is this number 3. So that's going to be part of our greatest common factor. As far as our variables go, we have x's that are common, and we have at least one, and it looks like 2 y's that are common to each factor, each term. So what this tells me is that the number 3xy squared is the greatest common factor, and what's left behind from our 12x to the 4th y squared happens to be 4x cubed, and that's it. What's left behind with our negative 6x squared y cubed is the number negative 2, so we'll write minus 2, an x, and a y. So negative 2xy. And then from the 15xy squared, a 5 is left behind, which is positive, and that's all. This would be our factored answer using the GCF for this original trinomial. We have two sets of homework problems to complete tonight, and following this first part of the video, these are the problems that you need to complete to go along with them. Each of these problems will be examples of factoring numeric and multivariables GCFs. Next, we're going to discuss just a little bit more about factoring using the GCF, and we're going to talk about the idea of factoring completely. Factoring completely. We want to make sure that we factor a trinomial all the way down to its most simple form. Again, we're looking for binomials. We want to see binomials at the end, so we're going to try to do that here with a couple of these examples. Having practiced factoring by using the greatest common factor and showing this method here and this method here, we can find the greatest common factor by looking at prime factorizations of each of our terms. However, I'm not going to require that you show that for your work, because I think at this point you should be able to identify prime factors just by looking for patterns. So in this example here, if I had 4x squared minus 36, and I ask you to find the greatest common factor of these two terms, you should recognize that that's going to be the number 4, because 4 is the only number that can divide both of these terms. When I do divide or factor out the number 4, I'm left with an x squared minus 9. While that looks like an okay answer, you should also immediately recognize, based on our prior work, that this term left inside the parentheses here is a difference of 2 squares. And we can factor a difference of 2 squares using a technique that we discussed 2 weeks ago. So when we consider a result to be factored completely, that means that we've factored all parts and we've brought them down to the most simple binomial that can be left behind. Here, since x squared minus 9 can be factored into x minus 3 and x plus 3, then we need to go ahead and do that. And also bring down the number 4, since it was a greatest common factor in the step above. It doesn't disappear between lines, it has to keep being brought down. And here we have a final solution, 4 times the quantity of x minus 3, x plus 3. In this second example of our factoring completely problems, we should recognize that 2 is the GCF for this group. 2 is the largest number that can divide each of these three terms. And after I factor out a 2, I'm left with x squared plus 14x. Oops, sorry, that's not 14x. That should be a 7x plus 12. At this point, we should double check to make sure that this problem is factored completely, and you should recognize by now that it's not, because this trinomial can be factored into a pair of binomials. Since it's a standard binomial at this point, I know that x and x goes in the beginning of each of these binomials, and the numbers that multiply, the integers that multiply together to equal 12, but add together to equal 7, are both positive numbers. One's a positive 3, and the other is a positive 4. Here is a completely factored solution for this example. I have two more examples that come from example number 6. So let's start with this one here, number 1, 12x cubed minus 75x. We should recognize at this point that there's both a numeric and a variable that can be factored out as a greatest common factor. And the largest number that divides both 12 and 75 happens to be the number 3. And we can also factor out an x value from each. And if I factor a 3 and an x from both of these terms, the 3 factored from 12 leaves me with 4, and this x factored from x cubed is an x squared. Then the 3 factored from 75 leaves us with 25, and the x factored from x leaves us with nothing else here. X divided by x is 1, so essentially that disappears. We have 3x, that's our greatest common factor, and the remaining portion inside the parentheses here can be factored again because it's a difference of two squares. This becomes a 2x and 2x with 5 and 5, 1 plus sign, 1 minus sign, and we have a factored answer for part number 1. Here in part 2, I've got another example. Here in problem number 2, I have a trinomial, 36x plus 4x cubed minus 24x squared. And in this trinomial, we have both a numeric and a variable portion to our greatest common factor. The largest number that divides 36, 4, and 24 is the number 4 itself. And the largest quantity of x's that can be divided or factored out of each term is 1x. So, if with the numeric value of 4 and the 1x that's been factored out, what's left behind is a 9 plus x squared minus 6x. We should rearrange that trinomial on the inside of the parentheses here. Let's call that x squared minus 6x plus 9. And doing so this way, we should recognize now that we have a standard trinomial that happens to be perfectly square, because the first term and the last term each have square roots. And when we factor this problem, we're left with an x minus 3, x minus 3. When coupled with the 4x that we had out front from the line above, this is a nice final solution for the greatest common factor in standard form for this particular example. We'll go ahead and skip example 7 and 8 right now in the interest of time. We can talk about those in class tomorrow. For your homework tonight, for the second portion of your homework, I want you to complete these problems here. So basically we had all of the even problems from group 1 through 16, and what we have here are problems starting at 19 in this group, and we're increasing by 3 each time. Please have those prepared for class tomorrow. We'll see you then.